Hey there, in this video we'll be looking at the first C++ interlude in the walls and mirrors data structures text. And this first C++ interlude gives you a review of the basics of using C++ classes. So what we'll be doing here is thinking about smart ways to design and organize several interrelated classes that kind of do similar jobs and you expect to use them within the same program, and what are some smart ways to get that set up. So we'll look at this in the context of a problem to solve, like kind of a simple video game where a character may be carrying maybe one of three different types of boxes. So the three boxes that we'll be designing here will be, number one, there's a plain box that just carries one object inside it. And the idea is that it could be any kind of object. It could be an integer, it could be a floating point variable, could be a character, could be a string, could be a rectangle, could be an inventory list, could be a car, could be a vector, really any kind of object, just one object being carried in your plain box. Now, number two, there'll be a toy box that does the exact same job, but in addition is painted in some kind of bright color. And then number three, there'll be a magic box that, again, kind of does the same job, but has a special trick whereby if you put a second object in the box, it turns into the first thing that you put in the box. So we'll think about how to, if they're kind of doing sort of largely the same job, how can we structure that to not be duplicating or repeating a whole bunch of code there. So let's start with the plain box design. So here's the starter, the initial try at a header for the plain box class that we get in the book here. So this is just a header file. So this would be in a file plainbox.h where we define our class. Now, the plainbox class is intended to be able to carry any type of object. So what they're doing as an initial stab at this, as they suggest in one of the appendices of the book, is they're using a type def to begin with. We'll say, let's say that we're carrying a double precision floating point value in the box, and we're going to give that a unique name in this file. We'll just call that item type. So as you can see, this class has one single data field. It's in the private section, and the type that will be indicating all through the code, we won't actually say double, we'll say item type. And in this case, the member is called item internally. And what that allows us to do is that for the program to carry around something else, we can just go back to line 7 here and change double to int or rectangle or car or whatever we need to carry in this particular box. So that's how they're going to do that. We'll think about whether that's the best way. So our plain box has just one single data item of type item type right there. And then next you'll see the public functions. No big surprise here. There's a default constructor that just sets up the plain box to begin with. There's a plain box constructor that takes in the first item to be stored. Notice that that is being passed as a constant reference so that you don't have to spend extra time getting into this function. And then there's a mutator called setItem that when you want to put a different data item in the box, you just pass it in and setItem sets it up properly. And then there's an accessor called getItem that looks at what's currently in the box and just returns a copy of it. So kind of standard stuff. Again, hopefully this is very familiar to you after a little bit of object-oriented programming of you have your private data, you got a constructor, you got an accessor, you got a mutator, very similar to other examples hopefully you've seen before. So think about the basic elements that should be familiar from your first object-oriented programming class that we just saw there. The data field is private, of course. You're going to have several, probably one or more constructors. We didn't see a destructor there. If we were doing any kind of resource allocation, like dynamic memory or opening a file handle or something like that, we would need a destructor in order to gracefully close it. In this example, we saw a default constructor, we saw a non-default constructor. Frequently, you'll also see a copy constructor that'll come later on. You're seeing some member functions. Remember that in C++ speech, we usually call those things member functions of the class. In other languages like Java, people like to call those things methods for short. So in this textbook here, they frequently say methods. We'll go back and forth between saying member functions and methods. Keep in mind that's just the same thing. Of course, our member functions were our accessor, our mutator there. For our header files, you have to have those preprocessor directives, the if it's been defined, if it's not been defined, and stuff like that. And we always see those include guards in our header files to protect against a compiler error that could happen if you include that header file twice in some particular file, which is actually pretty common and in some cases impossible to avoid. So the include guards protect us against a particular compiler error. And then we're also using that type def there to set ourselves up, creating a new type called item type for whatever the box is carrying, and that's setting us up to be able to change it easily when we need to later on. Is that the best possible choice? Maybe not. Maybe we'll think about something that we could do better than that. What could we do better than that type def? So before we get to that, here's the implementation file for the plainbox class. And of course, the definition we have in plainbox.h. The implementation here we're probably going to have in plainbox.cpp. That's just conventional. And so you have to include the header file so we know what the definition is. Here, the default constructor doesn't actually have to do anything at all. The non-default constructor takes in the item, right? Takes in whatever item you want to specify to contain and just makes a copy of it. Just copies the thing that you passed in to the private data member that's called item. Okay, pretty standard. You have your mutator set item that does that exact same job. And then you have your accessor get item that just returns whatever is in the current private data item member. Notice that that's making a copy, right? You're looking at item and then you're returning what's actually a copy into the return value. There's quite a bit of copying here in your assignment statements and also this return value that's happening right there. So, a very small little example of what you need for a basic class. Okay, so now we're going to think about what could we do better than using the type def to make the thing that you're containing changeable. So the problem with the type def is that when you need to change it, you actually need to go change the code. You need to copy that code file, copy that piece of code, or change it to get the plain box to contain a different thing. So what would be better than that is allow the client programmer to specify what kind of thing they want to hold in the box. And if you want to do that, that's what a template is for. So here, we're going back to plainbox.h, the definition header file, and instead of the type def, now we're going to make this a template class. So we're adding the template header here, and what's going to happen is the type of thing that you're dealing with now will become a generic type that the client can specify when they instantiate this plain box. Now, in our prior course, our habit, for what it's worth, was to make the generic type always just capital T, is probably what you saw in our prior C++ programming course. That's what we did there. Okay, some people do that, but again, it's probably better to have a more full description, more full name. So what you're going to see here is the generic type is not just being called T, it's called item type. Here's the item type that you're storing in this particular container class. Okay, so template class item type, that's the type you're going to be dealing with that's specified by the client when they make one of these things. So basically the rest of the header file is no different at all. You've got a member data of this item type and everything else is exactly the same. So there's a non-default constructor that takes one of those things. The mutator takes one of those things, and the accessor returns one of those things. Let's look at, okay, there's line 28. We're going to come back to that in a second. Just think about that. But let's look at the implementation file. So this is what the author of our textbook has put into plainbox.cpp for the templated version of this. And you can see that now all of the functions have to get the template prefix to indicate whatever actual type you're working with. And now the full name of the class becomes plainbox angle bracket item type. Specific, and technically if you make multiple of these holding different types of things, you have different types of plain boxes. You have a plain box for integers, you have a plain box for doubles, you have a plain box for rectangles, et cetera, et cetera. So you've got a bunch of different of these if you need it. So there is the default constructor, there's a non-default constructor, and then basically other stuff happens for your accessor and your mutator. Let me focus on two kind of important things on this slide that are going to be new here. Number one, if you look at the non-default constructor on line 10, so you're working in plain box whatever item type class, the name of the constructor is plain box, it takes one of these items, and you notice that when we do the assignment, previously when we do the assignment into that data member, that's been changed here to use what's called an initializer. So we don't, in the body of the function, we're not seeing item equals the item anymore. What they've done is on the function header line, you've got a colon, and basically what they're doing is they're effectively calling the constructor to that aggregated subobject. So whatever the item is, that's the name of the data member, of course, just pass into it the item that you're getting as the argument, and that's going to store the item in item is what's happening there. So technically, you could do it either way. I don't think we ever saw one of these constructor initializers in our prior course. It's actually not in the textbook. But in modern C++, what you're seeing here is the recommended way of doing that. And there's a little technical reason for that. Here's why. If you do your construction with a normal assignment, technically, the object does have to get laid out in memory someplace first. And when that happened before, all that initial memory got filled in with effectively zeros. Then you get into the body of your constructor, and then you copy in the new item into that space. So technically, you've now set it up twice. Once with a bunch of default stuff, and then a second time with your actual assignment. So you're kind of duplicating the effort to initialize the object. What you're seeing here with the initializer is a special way of communicating to the compiler. No. Use this for the first thing when you actually set it up. So now when C++ sees this and constructs your object, as soon as it gets laid out in memory, you get a copy of the item and you don't have to duplicate that work. Now, as a little bit of personal opinion, I'm not super happy about how this looks. To my eye, this looks weird compared to normal assignment statements. So I'm not super thrilled about seeing this. If I compare to the Java language, Java deals with this same issue without this new piece of syntax. In Java, if I recall correctly, just the first couple lines of a constructor function automatically know to do this, and they look like a normal function call. But here in C++, you have this special piece of syntax to actually really set up memory this way the first time. And this is nowadays the best thing you can actually do for your constructor setup. Now, the second thing I'll point out is look at up on line 1. They're putting this code in plainbox.cpp. So I hope you recall from our prior programming course when we were talking about template classes that there is a difficulty about where to put the implementation code for your template functions. And we like to separate, right? We like to separate out the definition from implementation, okay, in two files frequently. But the problem is the C++ compiler doesn't really know what to compile for a template function until it sees a function call being used, and only then does it know what actual type to start compiling internally. So the problem is if you put all your template functions in a CPP file like this, and it attempts to compile that, there isn't actually any code produced from the independent CPP file, and it cannot make normally a .o object file that gets linked in later. That's impossible and doesn't actually produce anything. So now you have a problem. These CPP files like this won't actually successfully compile to their own object files. So I noticed that if I look in the book here in section C 1.3, the author of the book has to put this special warning about this issue. So there's a programming tip here that says, in your development environment, do not add the implementation file, plainbox.cpp, for example, to your project. It will instead be automatically included by the compiler when it's needed. So why is it being included by the compiler when it's needed? Let me go back a slide, actually. You notice at the end of the template header file, line 28, it says #include plainbox.cpp. I bet you've never seen something like that before. But what that's doing is it's just taking where the implementation code is, copy pasting it here. And so when the compiler finally sees this, it looks like all of the code is in the header file. And that's actually what we said in our prior course. We said you got to put all the implementation code in the header file for template classes. And that's effectively what the compiler sees when you do this little trick. Okay, so last course for us, we just said literally type all the code in the header file, be done with it. Here, the author of our book, and I respect this, really for conceptual purposes, wants to separate out the definition from the implementation in two separate files, and here's how they're doing that. But to my opinion, it still becomes really awkward because now, like they say, you can't add plainbox.cpp to your project because when you hit compile, for example, dev C++ assumes you want to compile CPP files to individual object files. It's actually going to produce a compiler error because it's going to be scanning plainbox.h. It's also going to be scanning plainbox.cpp. And since you copied this stuff, since you included this stuff by the include statement, it's going to complain that you're defining these functions twice. It's going to see these definitions twice and throw up a compiler error. So as a result, you can't put plainbox.cpp in your project. Now, they're right. If you avoid that, you can get the project to compile, but I find it pretty inconvenient that you don't have it in your project list and you can't just click on it to bring it up whenever you want to. That actually becomes kind of a workflow problem. So there's a bunch of different strategies that people have used over the years for this. One common strategy is to put your template function code not in an H file, not in a CPP file, but to make up some brand new extension just for this that the project doesn't try to automatically compile and fail. Some people will use an extension of .tpp for a template in C++ file. I've seen some people use a .inl file for inlining, which is effectively what you're doing. I've seen some other strategies. What we're probably going to do in our course is we're not going to put this stuff in CPP files. Instead, we'll put it in .hpp files. And what that'll do for us is our IDE dev C++ will recognize that as a code file. You'll be able to add that to your project and then be able to kind of click on it and access it conveniently. And it will avoid the attempt at automatically compiling it to an object file that will fail. So for us, dev C++ knows that's a kind of header file. We've got a different extension, so we know it's not like a .h file that has class definitions in it, and I think that'll be a lot more convenient for us. Again, there's so many different strategies to this. It's honestly a little bit of an awkward issue in C++ that you need to deal with this. I believe the current Google recommendation is just don't even try to separate it out anymore. Just put all the template code just in the original header file like we did in our last semester, and that's the current Google recommendation. But we have it split up in our textbook here, in the Walls and Mirrors textbook. I understand the motivation for it. Honestly, separating those is fundamentally a good idea. So what we'll probably do in our course is switch all of these files to .hpp files. And of course, if you go back, then you'll have to be including plainbox.hpp, and that's probably what the code looks like when you get it from our learning management system. Okay, so there's a little thing you got to deal with in C++. Wish that wasn't the case, but there it is. Okay, there's the rest of the implementation code to the template version of plainbox. Basically looks the same activity for all the other stuff. What else? Okay, now that was plainbox. Remember, we got 3 objects that we're trying to construct here. So for the second type of object, the toybox class, remember that it mostly does the same stuff as the plainbox class, but also has a color to it. So what we would like to do is avoid duplicating, avoid repeating all that code that already exists for plainbox, and this is where inheritance comes in. So what we're going to do is we're going to use plainbox. You might say base class, some people say superclass, I tend to say parent class. And what we'll be doing is we'll be defining toybox as a derived class or a subclass or a child class of plainbox, get all the stuff that's in plainbox for free, and then add information about the color of this box. So remember, hopefully this is a review, a derived or a child class is going to inherit all the data members of the base class, all the member functions of the base class, with the exception of the constructors or destructors. Constructors or destructors actually get called automatically, but you will need to have your own constructor or destructor in your class if there's extra stuff to do. Let's take a look at that. So here is our definition to the toybox class. This is our header file in toybox.h. You have to include the plainbox definition to get to know about all that stuff. And the important thing here on line 10 is you're making a class called toybox, it's based on a public version of the plainbox class. Again, of whatever item type we're templating for storage purposes. So having done that on line 10, you have the same item, private data member, you have the same get item accessor, you get the same set item mutator, you get all that stuff for free. We don't need to repeat that. But what we do need to do here is add stuff about the color. So they've made an enumeration for the different permissible colors that you can see here called color. And the thing that we're adding to this toybox class is you have a second data member of type color that's called box color. And then you have to specify the toybox default constructor, a non-default constructor that takes in the color that you want to paint the box, a toybox constructor that takes both the starting item internally plus the color, and then we're adding an accessor here called getColor that just returns the color. Notice that they didn't put in a set color. I would say the color of this box is immutable. Once you construct the box at the outset, you cannot change it again. There's a lot of objects in the world. There's no reason to change it. So they didn't bother to give you a set color. That's actually pretty common. Here on line 21, again, it's a templated class with this generic type that we're calling item type. So the implementation there, we're going to put in a separate file. We have to include that to make the templates work. And again, the book, it wants to call this toybox.cpp. We will probably call it toybox.hpp, which will work a little bit better in our IDE. Let's take a look at that. So here is the implementation code for us, probably toybox.hpp. And here is your default constructor. If you don't specify anything, you just get a black box using that initializer on the constructor. Here's a version that does stipulate the color when you construct it, using that initializer there. Here's the version that specifies both the initial item inside plus the color. So here they've got there's 2 initializers, of course. 1 to set up the item, 2 to set up the color. Notice if you have multiple initializers, there's a comma separating all the initializers. I think if you're using initializers like this, much of the time your constructors might wind up having just empty bodies, and you might have a longer and longer initializer list is what this might start to look like. Not my favorite thing to look at, but that's what modern C++ looks like. Here's your accessor to return the color. I think that's actually it for the toy box class. So kind of nice that by using inheritance, we got all the stuff from plain box for free. And don't forget that toy box has a get item function, it has a set item function, and they work exactly the same as the plain box. And we didn't repeat ourselves, which is the important thing. So very smart about that. Now, what else can you do when you're setting up a class hierarchy with inheritance? Well, you can add any new members you want to the derived class. You can add as many member data fields like that color as you want. You can add other new functions like that get color, as many things as you want. You can also redefine how the inherited methods work. So if for some particular purpose you don't like how get item works for toy boxes, you could redefine that to work a different way than it did in plain box. So this is called overriding a base class method. And technically a method overrides a base class method when the two methods in the two separate classes have the exact same name and the exact same parameter declarations, or what I would say the exact same signature. That's what we call overriding. So let's take a look at when you might want to do this. So here is our header file for the Magic Box class. And remember, Magic Box kind of looks like a plain box, but it does a trick whereby if you put a second item inside, it turns into the first item that you had inside. So what we're going to do here is we're going to define the Magic Box class, again, base it on the plain box class, so you know that there's an item data member, there's a get item member function, there's a set item method, there's all that stuff you get. But the trick is going to be, we're just going to set a flag about whether you ever stored a first thing, and then when you try to store a second or third or fourth thing, okay, the trick is you just ignore it. You just don't change what's inside it at all. And then if you put a second thing in and look inside it, it looks like it turned into the first thing. But really, we never put the second thing in the first place. So what you're going to add here is a member data, a Boolean that just flags whether we've stored a first thing or not. Because we'll let you store one thing and then not let you save anything after that first thing. So here's the definition to the default constructor and the non-default constructor. And you can see on line 16, we're going to redefine the set item function. Exact same return type, exact same name, exact same argument that you first saw in plain box, but we're going to rewrite this to do something slightly different. Again, here's the include that you need for the separate file that you're putting the template implementations in. Okay, so you're going to see that a lot in this course. All the containers we ever work on will be template containers, and we will use this same separation all the time. So here's the implementation file for the class Magic Box. You've got the default constructor that, if you don't specify anything to begin with, will set first item stored default. Haven't stored anything yet. Then in the non-default constructor, if you get an item, all you got to really do is you call set item, and that's down below here. So what set item does, and here's where the magic trick is, you pass in some kind of item. Now, if you have already stored a first item, if first item is true, you skip all this code you're looking at and just don't do anything. You just leave the first item that's sitting in the box unchanged. Only if you have not a first item stored, if you've not stored a first item, if first item stored is false, only then do you get into this code here and actually call the original plain box set item that really does store an item there, and then set the first item stored to true so that never happens again. Okay, so there's a little trick that makes that happen. But the important thing is now we have two different set item functions in the system. We have the set item for plain box that just always copies whatever you tell it. And then we have set item for Magic Box that ignores that after the first item gets stored. Two different versions of that. That's overriding or redefining a function that you've inherited from a parent class. Okay, so if you're overriding functions like that, here's a little reminder about some other stuff you probably want to do at the same time. Number one, you probably want to use the virtual keyword on the original definition on the parent class of that function, so the system knows that you're going to be redefining functions and it's going to have to handle that. What that technically does is it tells the C++ compiler the code of this method that you're executing needs to be determined at runtime. You can't just link it in with the compiler. You're going to have to do extra tracking when the program runs to figure out which of those two versions of the function to call. Now, if you're doing that, then, and you know you're going to be making inherited classes, then you could just skip giving any code in the parent class because you know you're going to override it later in the inherited classes. If you do that, if you skip giving any code in the parent class, that's called having a pure virtual method. And when you do that, that method doesn't have any implementation in the parent class. You're just waiting for the child classes to see what they need to do about it. When you do that, when you have one of these when you have one or more of these pure virtual methods, then the class is referred to as an abstract class. And what that means is that you actually can't instantiate an abstract class because some of the member functions are missing code. And so that's, we frequently do that in a sophisticated class hierarchy, again, as an initial route to set up what the child classes need to do to be compatible. So leave out the code on any one or more functions. You have an abstract class, and that only gets used to be a parent to some child classes. So here's what you could do. So knowing that, what we would more likely do, go all the way back to the beginning here, and at the outset, what we would probably do is we would make an abstract class like that to be the parent of all the classes that we're talking about. And the purpose of this is just set up the signatures to the functions so that all the classes match and are synchronized and doing the same thing, basically. So here is a header file that we'd call boxinterface.h. When you're setting up one of these root parent abstract classes, people frequently call that an interface. And specifically in Java, that's actually a structure called interface. It's actually a keyword called interface for exactly this kind of job. So if someone was doing this kind of work in Java and then moving over to C++, it's very likely that they would call all this stuff boxed interface, which is exactly what's happened here in front of us. So you have a template class called boxInterface. It has no private data whatsoever. We'll leave that to the child classes, and it's setting up what kinds of functions you need. You're going to need a mutator set item because we've seen that a couple times. You're going to need an accessor called get item because all the classes obviously need that. And then when you are doing this kind of thing, it's required that you do specify a destructor specifically. You don't need a constructor, but you do need a destructor in the parent root class. Otherwise, at some later point, when the destructors get made, they don't link up properly if you skip that. So you need kind of at least these three things. Notice there's no CPP file, there's no implementation file, there's no implementation code for any of this stuff. It wouldn't even make sense because there's no data member here. At the end of the function signatures, there's this equals 0. That's the signal that you're not giving it any code, that it is a pure virtual function, that you need to wait for child classes. And then you do have the initial keyword of virtual that indicates we expect to override these things in a later class. One option would be you can have virtual functions that do have code that you'll change in the child classes. What we're doing here with the equals 0 is this is a pure virtual function that you need to override in a child class. So that's probably what that's going to look like most of the time. And then what you do is you take this as your top-level parent class, and then we should rewrite plainbox to inherit from this. And plainbox is where you get your first piece of data member, actual code to the functions, and then other stuff can inherit from that. So ultimately, everything is inheriting the specifications for the function signatures from this master parent class at the top of the chain. So then, having specified virtual member functions all the way through the chain, then we can start using polymorphism while the program's running to call the correct version of the different functions. So that's what we're going to do when we review Interlude 2 later on. So hopefully we will be seeing you, hopefully you can join us for our next video, which will be on Interlude 2, using polymorphism to make use of these virtual functions, and I hope you'll join me for that.